Well, hello everyone. It is week 14, I guess technically 15, but if I call this week 15, people get confused on YouTube and say, where's week 14? So it's week 14. It's our last class, and by request, I'm going to try to cover some basic techniques for interactivity. And now we've kind of talked about interactivity a little bit. It's kind of been an underlying thing this whole semester just because of how SuperCollider works with sound on demand and with live coding and stuff. There's many ways to interact with SuperCollider, and there's many paths along which you can pursue interactive music. So live coding is one. Dealing with MIDI controllers is another. We didn't do an OSC lecture this semester, but I have many videos on OSC and using your phone or a tablet as a controller. But one thing which I've never really covered in this class are the various feature extraction unit generators, things which track amplitude, which track pitch, which track articulations, onsets, transients, timbre. Right, yes, very exciting, I know. So the first thing I want to do before we get into code land here is I have this scan of a page from chapter 15 of the SuperCollider book, which there is a version 2 coming out very, very soon. I don't know exactly when, but it's a lot of people have been working on it. But this is from the first version, which was published back in 2011, chapter 15, written by Nick Collins, who's also one of the editors of the volume. So he's a very experienced user and developer. And so this page is just a table of the various machine listening unit generators. So we see a category of type of musical feature we want to track, and then various unit generators which track that information. So amplitude, pitch, timbre, onset detection, and then a couple of higher level things like beat tracking and key tracking and things like these. I haven't used a lot of these. It's I've used amplitude, I've used pitch, and I've used a couple of the onset detection. And really just those can take you quite far with the types of information you can capture in real time, and then the sky's the limit regarding how you actually want to use them. So what it's quite a day, a lot of stuff going on today, so I'm feeling a little bit less prepared than I like, but sometimes I do my best teaching when I'm underprepared. So I'll let you be the jury on that. But what I thought we'd do is first look at some code which simply tracks information from my voice. So we're going to be feeding my voice into SuperCollider. So you're going to hear a double voice because of the way things are set up, because I have my microphone going straight into my recording software, but then if we also pass it through SuperCollider, I think there's going to be a tiny amount of latency, and so you'll hear kind of a double voice. I could mute my direct feed and then just rely on SuperCollider, but I am inevitably going to forget to reinstantiate my sound in unit generator synth, and then I'll be talking and there'll be like 15 minutes of silence in the video, and I'd rather just have the double audio than risk me accidentally being on mute for like half the lecture. So just keep that in mind. You here in the classroom are just going to hear one voice, but on the recording you'll hear a double voice probably. So let's boot the server, and what I've done here is allocate several buses. We'll come back to these in just a second. And I'm just adding a single synth step, which I'm calling track, which is going to be responsible for grabbing the microphone signal and then just really capturing a bunch of data. We're going to get rid of that for a second. So I have a variable called amp track, which is using a unit generator called amplitude, and pitch track, which is using a unit generator. So it looks very simple, doesn't it? You just feed in the signal you want to track. And I'm using onsets, which in the past I've used PV Hainsworth foot, and that worked pretty well too. These all, I think they work pretty well. The idea is you've got a sort of buffet of feature extraction UGens, and there's really nothing to be lost and everything to be gained by just tinkering and swapping one for the other and trying different settings. And within these unit generators, there's actually quite a few, maybe not so much in amplitude, but we have an attack and release time, and then our usual mull and add. Pitch has tons of stuff. There's lots of the different parameters. Why don't we look at the help file for pitch momentarily? So all things considered, pretty comprehensive help file. So here are our arguments, and then there's a lengthy discussion which kind of talks about each one. But just to give you, this is the tracked frequency that the UGen is initialized to. So it can default to 440 until it receives a value. you can bound the frequencies that it tracks, so it will just sort of cap out at max frequency, and just this helps you eliminate bogus data. Like if some high-pitched thing is in the background or some low rumble, it won't accidentally give you that data. And then the other one that I will talk about is this clarity parameter. Pitch is a little bit different. Amplitude just outputs a single value, which is the tracked amplitude of the signal, more or less. Pitch will output an array of 2 values. One of them is the tracked pitch, if it is able to coalesce around something, and the other one is a 0 or a 1. And 1 means I'm confident in this pitch, and 0 means there's no pitch that I'm able to discern. So you could basically use that as a gate or a trigger so that you're not constantly tracking pitch, and instead you can sort of say, when this value is 1, let's use the actual tracked pitch, and when it's 0, ignore it. Clarity, if you set clarity to 1 instead of 0, then this whether I've found a pitch value has a little bit more precision to it. It's kind of a floating point between 0 and 1. You get the idea. And then onsets, we provide, this one's a little bit different in that probably this one is an FFT-based pitch tracker. Well, it might not be, actually. It might be an autocorrelator because it compares it to zero crossing. Whatever. Onsets is an FFT-based threshold detection unit generator. And so what we have to do is take the live signal and do a real-time Fourier transform of that. And it's going to use that Fourier data, this sinusoid decomposition, to determine when an onset happens. Some of them are very obvious, like if you have a snare drum, or you just go ka or something like that. But if you go, it might not find an onset there because it's a kind of gradual thing. But it's basically going to be you do an FFT, and the way you do this is this is the quickest way to do it. You use the FFT class, and you provide 2 things. One is a sort of a buffer. This is very much the same idea as b equals buffer.alloc, and like a buffer for sound files. But this one is going to hold FFT data, and then this is the signal on which to perform the Fourier analysis. And so what we actually get is not a time domain signal, but a real-time Fourier analysis of that signal. And then we give ourselves a threshold. I think this is just the amplitude, perhaps, of that the analysis needs to exceed in order to say that's an onset. So you can lower this to make it more sensitive and raise it to make it less sensitive. And then this is just various algorithms. Like we can read about this. This is I think this is I don't want to. Yeah, Dan Stoll is one of the authors of this unit generator, and the ODF type is just choosing which onset detection function is used. So basically, different algorithms in a sense. And I think R complex is the default. Yeah, default is R complex. OK, so what I'm doing here is then just writing these control data to control buses. And that's what I've allocated up here. So amplitude, I know this UGen spits out a 1-channel signal. Pitch, I know, spits out a 2-channel signal. It's the frequency and whether it's found a frequency or how confident it is in that frequency. So that's why the pitch bus is a 2-channel control bus. And then this transient bus, I went back and forth with my naming here. I was calling this onset track and then transient track. So that's why it's called transbus. Just a 1-channel. And what this UGen outputs is a control rate trigger signal, which is 1 when an onset is detected and 0 not. So it's like ready to use as like an envelope triggering signal. So let's and then I also I'm also passing the what we could do here is just write the microphone signal straight out to speakers. We can always comment this out if we don't like it. So if we do this and then just run this, you should that's okay. That might be my interface being a little clunky. Let me quit the server. I've had this problem before, and I don't know exactly why the audio is so yucky. But let's see if it's a little better. OK, it's happy with that. Let me turn this down. Let's make a amplitude. All right, do this, and check. Yeah, still coming out. OK, just trying to minimize feedback risk here. All right, and maybe I don't want to listen to myself right now, so let's. OK, so now the synth is active. We're just bypassing the audio signal going through. Let's start by just visualizing the data in various ways. So we'll pull the amplitude tracking signal just to see what we get. So command period, reevaluate the synth def, and then there we go. So now what we're looking at is the tracked amplitude. So if I stop talking, you get a really quiet value. And if I go, right, then we can hear some data. And let's go over to the scope and just look at one control channel. And this is the tracked signal. Hello, amplitude, blah, 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 blah. Right? So that's working. So it's just basically a number, 0 when it's quiet and closer to 1 when we get louder. And one thing that you may want to do with this and many other control signals that are tracking real-time features is smooth it out a little bit. And maybe also scale it. I mean, I always find this amplitude value to be lower, closer to 0 than I think it should be. So you can always, I don't know, just multiply it by 2, multiply it by 5, whatever you like. I mean, it's just a number. So, but let's also smooth it out and try to make it a little bit more, so it's not quite so jagged all the time. The way I like to do this is by lagging the signal by some amount. So lag, we've seen lag before in this class, right? It's just it's essentially a low-pass filter, right? That all it does is it just makes a jumpy signal a little bit less jumpy by specifying a time interval over which to basically average the data. So I'll say 0.05, 20, 50 milliseconds or something. And let's also just multiply this by 4. And then we're pulling it down here again. And we'll take a look at the scope or control bus. And now it just feels a little better to me, just looking at it. So that's, we can always come back to this if we want. And something else we might want to do is snap it to 0 if it's quiet enough. And we can do that with a sort of server-side conditional logic. We can, in fact, why don't we, let's see. So we're polling it. What I want is when we're, sufficiently close to 0, say less than 0.002, then just set it to 0. And that'll give us a sort of cleaner, like actually silent signal. Let's command period that. And here's the first thing that occurs to me on how to do this. A limiter wouldn't, no, yeah. So, but there's a unit, okay, so I have a mini tutorial called using if in a synth def. And the spoiler of that one is you can't really use if in a synth. You can't use regular language side conditional logic in server, synth defs and things like that because, well, you can watch the mini tutorial if you want to read about that. But the not necessarily the computationally most efficient option, but the easiest one is a UGen called select. So select, you give it an index and an array, and it will output the unit generator at that index. So what we can do here is say for the index, we'll say is amp track less than 0.002, right? So this, normally in the language side, this would be some fixed number, and this expression would return true or false. But on the server, conditional, comparators like this return 1 if true and 0 if false. So, the reason you can't use if on the server is because the answer is not known, because the things you're comparing are dynamic signals, and so they might be true, they might be false, so we have to wait and see and be constantly evaluating. And so if this is true, then this expression will return a 1. And if it's so true, in other words, we're quiet enough, this becomes a 1, and so we want to use 0 as the item at index 1. And if it's false, this returns 0, in which case we just want to return the signal. So amp track, comma, 0. Yeah, so you see this is, if this is false, right? If amp track, if you have a substantive value, false means 0, and so we return the 0th item, which is whatever that value happens to be. But if it's true, then we're going to say, okay, we're going to return the item at index 1, which is 0. And so now if we run this and run this, hello. Yeah. And so we can tweak this threshold. It's basically you want to, you want to talk quietly and do the quietest thing that you want to register and make sure the numbers change. And so, maybe we would, obviously you can put a, something like this here. This probably, arguments are your friend, use arguments. So we could say thresh 0.005. Check, check, check. Woo, woo. Right. So that seems pretty good. What we're doing here is what I usually call cooking the data. Right? When you're making dinner, you don't just want to eat the raw ingredients, right? You need to cook them, and add some spice, chop off the ends of the green beans and whatever, right? So that's kind of what we're doing here. And so you might want to use gates, use this select, manipulate the numbers a little bit so that they suit your needs. It's rarely the case that you can just do something like this and say, good enough, right? Let's get cooking, right? So you need to, or let's not get cooking. So anyway, that's amplitude. Why don't we take a look at pitch now, just to understand what that is. So we will go here and say pitch track.poll and run this. I'm hitting command period every time, and so okay. So as soon as I start talking, it finds a frequency. So if I go, ooh, it's it can be a little bit. Don't expect perfection. Right? It's easy to confuse certain pitch tracking algorithms by giving it a signal with a lot of harmonic energy, in which case it might misjudge the fundamental. But if you're having trouble with one, you can go back to this and try Tartini or Quitch or any of these other ones, and maybe you'll have many ways to do it. So let's see. We could read about pitch and see. Yeah. So according to the help file, some vowels are still problematic. For instance, a wide open mouth, somewhere between a as in sat, and I as in fire, See that, how it's jumping quite a bit? Yeah. I couldn't tell you precisely why it's doing that, but I think this is just like all algorithms you can define. They always involve trade-offs, right? You can get precision with one thing, but you have to sacrifice something else. And the same sort of thing happens when you're designing digital filters. It's like you can make them phase linear, but then you have a wiggly transition, blah, 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 blah. So yeah, just the bottom line is it does a pretty good job, right? But it's not going to compose your piece for you or something like that, So let's, yeah. So if we set clarity to 1, just to kind of show you how this data looks a little bit different. So now this array at index 1 is going to be a measure of certainty, basically. So if I go, ooh, it's pretty confident on that pitch. But if I go, it's like, 0.5, 0.6, 0.7. So it's kind of being a little bit, it's saying, use with caution. I don't know if this is the right pitch, something like that. So, okay. And, so just keep in mind that this thing that comes out of pitch is an array of 2 values. So if you actually want to use, you want to spit out the pitch, you would do, to actually grab the pitch downstream, you would grab the value on the pitch bus on the first, the 0th channel, right? Because the other one is more usable as like a gate or something like that. All right, so let's look at onsets. This one is not good to poll because it's outputting a control rate 1 whenever an onset is detected. So it's a signal which is like 99.99% 0, and just for a fraction of a second you'll get a 1. So if we do this, it's going to be mostly zeros in here, but maybe occasionally there's a 1, right? So it caught that one, but it's catching a lot more than that. And you can go over to the scope and take a look at, what is this? Look at just one channel, 0, 1, 2, 3. Yeah, this one. Yeah. You can shrink it down like this. Yeah. So there we go. What else? I mean, again, we can adjust the threshold. So I think if we make the mouse do this, then command period. Let's pull this actually, and not pull this. So now we're looking at the threshold. So if it's up here, then theoretically we will get fewer triggers. Like I'll really have to earn those onsets. I need to go back to my scope. 3, 1, control. So if the mouse is over here, it still seems pretty sensitive. So I might be misunderstanding something here. But if we go down here, it's very jumpy. It's very reactive. Yeah, and so it could be that this 0.5, this threshold is maybe it's a normal thing to do to set this higher than 1. I don't actually know. Why don't we try? Let's make it 4. So now over here the threshold is very high. Check, 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 check. Ka, ba, ja, 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 ja. Okay, so yeah, maybe it should be around 1 for sort of maximum insensitivity. But there we go. So with all this data, let's look at some very, very simple and boring ways to actually use it in synthesis, and then I'll try to hack my way through something a little bit more interesting. But I just want to stress to all of you that there is no recipe for, I'm going to go very broad here, for making art, right? There is a recipe for extracting quantitative information from stuff, right? That you can do, but then the process of transforming that into cool, wonderful, weird sound art some would say it's not something that can really be taught. I mean, you just have to consume and digest and experience and listen and try and sometimes fail and stuff like that. So I'm not trying to claim that check these boxes and boom, you'll have an interactive piece. You have to come up with a concept and really kind of work to make. So okay, here we go. So why don't we just start by playing a little white noise burst when I'll have like a little percussive white noise thing follow my voice, like the onsets. So we'll track those, and then maybe we'll use the pitch to filter it and make it follow the pitch of my voice as well. All right. Again, feeling a little underprepared, so bear with me. Sometimes, yeah. We are going to make some white noise. And I think let's make this a medium short percussive envelope. Now it has to be at the control rate because all of this stuff here is at the control rate. In fact, I don't think these unit generators can run at the audio rate. I think just the real-time analytical nature of them means they have to sort of look at data over a longer period of time, and you can't know what the pitch is of something at the audio rate, because at the audio rate you're calculating something every sample, and one sample is not enough information to give you the frequency of that waveform. So if this were an audio rate envelope, it just no, I got it backwards. I take it back. I think it can be. You can have an audio rate envelope with control rate triggers, but not the other way around. You can't have an audio rate trigger controlling a control rate envelope. Okay, so it probably can be audio rate. Sorry, I take it back. But we're going to make a control rate anyway. And the arguments are done action, we're going to make it 0 because we want to be able to re-trigger this envelope. And the gate, or the gate/trigger of this envelope, is going to be the onset signal. And that is being written to trans bus. So, I mean, we could do in.kr, right? And but there is I forget if we've covered this, but you can treat a bus like a UGen, and I'm not trying to do best practice code here. I'm just trying to make it work. So we're just going to say the name of the bus here, transbus.kr, and then I think we just give it the number of channels and the offset. So it's just a one channel, and there is no offset. We might need the offset for the pitch bus to say, give me one channel, one offset from the beginning. Now this should be fine, keeping in mind that we have the threshold here. So I'm gonna set this threshold not to be the mouse, but make it like 0.75. Just sort of guessing here. So we'll do this, create our tracking signal, and then now one thing that occurs to me is I don't think this is going to be a problem, but the noise coming out of the speaker might actually trigger more onset. So we might get a kind of machine gun thing here. I don't know. We'll find out. Cha, 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 cha. We're getting a couple of double triggers. Ba, ba. And I think that's because of the speaker, actually. Yeah, so I'm gonna turn this off for hit Command period. So I think what's happening is my voice is triggering the first onset, causing white noise to come out of the speaker, and that is causing a second trigger. So we can further cook this data a little bit, so that we basically what you want to do is when a trigger is received, make this envelope stop listening for triggers for X amount of time before it turns back on. And now this I'm going to be really making up on the spot here, but I think we can do that with trig. All right, so let's change this around a little bit. Okay, so we'll call this our trigger signal. Okay, so we're grabbing our raw onset control signal, creating our source signal, and then right now it's susceptible to rapid fire triggers, but there is a unit generator called T trig, which let's look at the help file. When a non-positive to positive transition, trig outputs the level of the triggering input for the specified duration. So this will basically take our single control cycle trigger and extend it an arbitrary amount of time. So we input the trigger, and then you ask yourself, what's a sensible duration to basically deactivate the envelope? And like how fast do I want these triggers to come? And so that's the question. So let's just say 1/5 of a second as a starting point. Obviously an argument makes sense here if you want to be able to dynamically change that. So now this let's go 0.3 just for a little more safety. Okay, so we make this and we make this. So I think I need to extend this even more. Oh, you know what? I'm sorry, I totally forgot to do this. My bad. I was like, those triggers are definitely faster than 0.3 of a second. All right, once again. And now, detection. Part of this is also, setting the. I'm going to turn this off. Microphone gain. You want to set the microphone gain to be. It's hard to think when this is happening. Okay, but I have this collar microphone on, which is probably not ideal if you're using a condenser microphone or like a Bell microphone or something. So I don't, extensive. You can't just write the code and have the code be perfect. You also have to do the physical sort of audio engineering, hardware setup, and microphone placement and stuff like that. But it could be that my threshold is too high, actually. That might be the most reasonable explanation. So again, we just want to, let's go back to the mouse. Mouse x.kr 0 to 1 and pull that. And so now we'll just bring this over to 0.5 or something like that, and we'll try this again. Check, 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 check. Test, test, test. A little more sensitive. Detection, detection, detection. Hello. Okay, well, okay. You get the idea, right? It's working, and I've sort of there are cases when, like for like a percussive thing, you'll want it to catch lots of onsets, and for that you would definitely not use this trig UGen. So context, 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 right? You have to sort of ask yourself, what kind of musical situation am I working with? What specifically kind of data do I want to extract? And okay, yeah, good. It should be. It's the whole point, right? It's lots and lots of ideas. So let's do a bandpass filter. And what we're going to do is say pitchbus.kr, give me, we need to probably, okay, so here's what I'm going to try here. We're going to cook this data a little bit. And we're going to use a gate. And so what the gate behavior, a traditional gate is going to pass a signal if some condition is met and zero the signal and silence it if the condition is not met. But gate actually just holds the last value. when the gate closes, which is, I think, maybe it'll work for us. I mean, I guess the question is, if you have some signal which is pitched and suddenly it becomes not pitched, what do you want that control data to do? Do you want it to hold the last value? I mean, are you just going to ignore the value because you're going to use the 0 and 1 thing instead? So I'm just going to do this because it seems like an okay solution for now. So we up here, I mean, again, we can do this cooking up here. We can do it down here. I don't know if maybe it's significant, maybe not. We'll see. So pitch track. Oh no, hold on. So okay, so let me think about this. So pitch track is an array of 2 values, and so pitch track. I might have to change the size of my buses here, or make another variable. Let's say just pitch here. So pitch is going to be equal to pitch track at 0. No. Yes, that's the signal. That's the signal we want to track, right? It's the actual frequency value, and the trigger is going to be pitch track at 1 greater than some clarity value, like 0.85 or something, because we have this. We're turning on the clarity resolution attribute here. So this value will be not always 0 and 1, but it'll sort of fluctuate between this. And so we want to say if our pitch clarity value is, or our pitch, confidence value is sufficiently high, pass the signal. Otherwise, just hold whatever your last value was. So that's what's going on here. And then here, I guess if we want to just keep the 2-channelness, we can say, instead of outputting the uncooked signal, we can say output pitch and pitch track at 1, right? So I'm just sort of swapping the cooked pitch in for the uncooked pitch, right? The gated pitch is now being output where the ungated pitch output was previously getting output. Does that make sense? Okay. So then, why don't we let's go ahead and poll this for a moment just to see what it's looking like. Ooh. So it just holds that last value. Ooh. And then if I do some noise, theoretically it won't change. So if I go like, ooh, yeah, so it's that pitch. When I went shh, the confidence value was too low, and so it just kept holding the previous value. So I just trying to make sure we only get good values here. So this seems fine. Ooh. Okay. Very nice. So then here we're going to say filter, bandpass filter this white noise, pitch bus.kr 1 channel. So it's just going to read this, and it's going to not read this, right? And RQ, we'll make it, I'm going to rough in a value for mul, because as you know, you may know, when you have a very high quality bandpass filter, at least this algorithm of the bandpass filter, the amplitude's going to go down overall because we're just filtering so much of the signal out. So this, this is our mul value. So, and we still have our mouse for the threshold here, so I'll just keep that in mind. Yeah, I'm just clicking. So, I should make this louder. Yeah, let's make this 10, and let's make this longer. And I'm gonna. There might be a good reason to not make these simultaneously. Like there might be a sort of like initial bogus data output from a lot of these so it might, I don't know, it might like clunk at the beginning. It's doing it, right? Yeah. Okay. One thing we can do is, all right, so I'm gonna move this back into its own separate thing, just because I guess because the question is if you just start this, if I start this process and it's like listening for all this data and then I create the tracking synth, the very first control cycle might just be a bunch of wacky stuff as these unit generators are initiated or something. So it probably makes sense to create the tracking synth first and then produce a synthesis node which maybe fades in or something, because at that point you're definitely probably getting good data. It's kind of a management thing. But let's take away the envelope, and so let's forget about the. We're just going to output just a constant filtered white noise here. Just tweak this a little bit. We don't need this stuff or this stuff. Okay, so here we go, and so it works. Why don't we add the amplitude in so that it'll sort of get quiet when I get quiet? So that basically we just, instead of this thing we had here, we're just going to say sig equals sig times amp bus.kr1. And keeping in mind that we're boosting this value by 4. Maybe we shouldn't do that. We'll see. We can always boost it later on. So we'll do that, and here. Okay, so we'll just, this is maybe a good, you should just use ndef here, just because I'm tired of hitting command period all the time. I don't know. Okay, so let's do it this way. Okay, so we have okay, I think I hit command period because it's just muscle memory. Okay, but there's that, and now I think it's working, right? Yeah, it's just yeah, it seems quiet here. I've had this experience. I don't know. Amplitude is just kind of a low output thing. I'm being very irresponsible here, but and yeah, we might want to actually lag the amplitude more over a larger interval. So maybe, this is going to make it less responsive, but it will make it smoother. So again, trade-offs, right? So we'll do this and this and this. Here I'm using ndef. Yeah, let's ignore that, and then still hitting command period all the time. So I can't get it out of my muscle memory. Yeah. Okay. So it's working. It's very sloppy. It's very rough, right? This is not sleek, polished, interactive music. But from here, the challenge is to design more nuanced and subtle algorithms. But the possibilities are really, just two things I was working on. I said I was unprepared, but I did actually prepare some stuff. But this is stuff I was working on yesterday. This one here, I'm trying to make a sort of a reverb that I can feed into by making things loud enough. So I can do like quiet stuff which doesn't get fed into the reverb cycle, but then I can go yeah, and then the yeah will get fed into because I'm using the amplitude as an envelope gate, right? So here's a percussive envelope, and the gate is I'm using trig to say, is the amplitude big enough? And if it is, that's a trigger. Hold it open for 0.2 seconds, and so that triggers this 0.2 second percussive envelope, and I'm using my voice here, so I can just put it in. We could try this. Give this one a try. Yeah. Okay, so let's copy this over here. I'm so glad you're all so excited. Yeah, I'm writing your dissertation for you here. Okay, let's back up here. So I'm being really messy with like numbers and stuff like that, so I don't know if this is all gonna work, but so okay, so sound in, we're reading our microphone signal and multiplying it by this envelope, which is triggered by this amp bus. I want to pull the amplitude signal just to see what kind of we're working with here, and I want to stop polling this stuff. Let's just make this a 0.4, and we'll call it a day. And there's some other poll here. Yeah, this one. Don't want that. Okay. There we go. There we go. And now we're just tracking amplitude. And if I go, okay, we'll say 0.1. 0.1, I guess, seems good. So we have our, if this is above 0.1, trigger the envelope. And maybe I'll just like adjust the faders on the mixer behind me if we need to. And if I talk quietly, I speak very, very quietly into the microphone. Nothing happens until I get loud enough, and then so it's going in. I see some freaking out happening in the classroom. So then, yeah. I feel like this is pretty crude. I mean, maybe it would be better with like an acoustic instrument or something.
Like you're a robot.
Yes, I've cyborged myself here.
You're talking to the Wizard of Oz.
Yeah, pay no attention to the man behind the curtain. Okay. All right, so that was that one. And then I also have this one where I'm using, this is a delay, a dynamic delay line. So a delay line in which the delay time is changeable. This one is far more explosive than the reverb that I was just working with. This one's a little more dangerous, which is why I have this aggressive limiter and DC bias remover down here. So what's happening here is we, again, read the signal in, and the delay time is taking the pitch value on the pitch bus and then mapping it from some range that I arbitrarily chose. I mean, like I can go down to 80, 75 hertz or something, and I can go up, I don't know how high I can go. But this is like sort of a reasonable, I don't know, for my vocal range or something. We'll go down to 100 to 600. And I'm mapping that onto these numbers. So low values, me singing low pitches will produce large delay times, and then higher pitches produce small delay times. And I'm using this comb filter with linear interpolation to, I think I need to make this 2. This is the maximum delay time, and so if this is the maximum delay, I need to set this. And then we have our delay time, which is lagged to smooth out the data. And I'm doing a stereo effect here and just sort of making the delay slightly different in the right and the left speaker. This is the decay time, so it's going to take 10 seconds to decay. That's just being in this live sound situation makes me a little scary, so it makes me feel a little scared. So we'll do that. And then I was modulating the delay with a pulse wave that it was 2 channels out of phase. And I think let's temporarily just like not do that. We'll do that. This is, I was just messing around, and then like, okay, so we'll just say that's fine. And then this is a mixing operation. This blend is a shortcut for a linear fade operation. So it's gonna be 40% wet, 60% dry. And then we do I should really be using like the stage limiter that I showed last time too, as well, that quark. That's an option. But okay, so fine. Let's see. I'm going to be hovering over command period here as we run this. Okay, so we have our synth def. We'll take this, copy it down here again. Okay, so there's that. And let's do just this. We'll remove that if it's quiet, but okay. So okay, it's making sound. That's good. I'm going to give this a name. All right, make that. Nope, don't make that. Make that. All right, And woo. I think it's responding to the speaker. Yeah, I'm ready for it. When it does that, it starts to feed back, but well, okay, hold on. It's fun, right? Yeah, it's a lot of fun. The limiter and the leak DC, it's really preventing us from disaster. But what was, I'm going to turn this off for a second. What it was doing is when it would sort of latch onto some high frequency for some reason and do this fast delay time, and it's a comb filter, so that it would start resonating at a frequency equal to the inverse of this value, and that would trigger it to think the frequency is low again, and then it would jump back down. So there's probably some clever self-feedback thing you can do where it latches onto this, but then it causes itself to, yeah, it's just, I just thought it sounded pretty cool. It's just a live delay with feedback, and the delay time is controlled by the pitch of my voice. So let's do it again a little bit. Let's just play around with this effect. Yeah. All right. So it needs to be fine-tuned, obviously, and this is far from ideal. This classroom where the speaker is literally right behind me. So, But anyway, that's basically a very, very coarse and half-prepared introduction to feature extraction in SuperCollider. So, oh, well, good. You are you are all just the nicest people. So, thank you. Okay, I should probably wrap up here because I got to go prep for the concert tomorrow and set things up. So that'll be it. I guess we just have the final projects, which will be whatever. Yes, thank you. December 11th, 1 p.m. Okay, so good. Feel free to be in touch in the meantime if you want to run ideas by me or get some help or anything along those lines. And thank you for a great semester.
Thank you. It was really inspiring.